Hello everyone. This talk is on Vertex Fault-Tolerant Emulators, and it's a joint work with Greg Bodwin and Mike Dinitz. Let me start by defining a spanner. Given a graph G, we say that a subgraph H of G is a T-spanner if for all nodes U and V, the distance between U and V in the subgraph is at most T times their distance in the original graph. So our goal is often to have a sparse subgraph that approximately preserves the distances in the original graph. So for example, here in the left we have this dense graph, and on the right hand side we have a three-spanner of it that is sparser, and between every pair of nodes the distance is 3 times the distance in G. Now what is an emulator? It is similar to a spanner, but it does not have to be a subgraph. So in particular, again, for every pair of nodes, we want the distance to be at most T times the distance in G in the emulator, and we also don't want to underestimate the distance for any pair of nodes. So for example, here you see that we are given a graph G, and here we have a 3 emulator of G, and note that even if G is unweighted, the emulator often needs to be weighted. And now H contains some edges that don't exist in G. And it's easy to verify that between any pair of nodes, there's a path that is at most 3 times the distance between the endpoints in G. So the main question in the context of spanners and emulators is that given a parameter T, we want to know what is the minimum number of edges needed for a T-spanner or emulator for a graph of size n in the worst case. And there are some existential bounds known. In particular, for any k at least 2, we know that there are that any graph has a 2k minus 1 spanner with roughly n to the 1 plus 1 over k edges, and that this is optimal assuming the Erdős-Gersh conjecture. And I'll explain more about this conjecture later. But moreover, there's some equivalence between spanners and emulators in a sense that even though we have more flexibility with emulators, this does not give us a better stretch and size trade-offs in classical settings. And basically the size we would get would not be any better for emulators. But one message of this talk is that in the fault-tolerant settings, this equivalence no longer holds. And in particular, we can construct fault-tolerant emulators that are sparser than the equivalent spanners. And before I tell you what all this means, let me define what a fault-tolerant spanner or emulator is. And so let me start by some motivation. So spanners are usually used in distributed computing and networks. And the goal is usually to have a sparse subgraph that can be used for the purposes of communication or routing. For example, here, let's say I want to construct a 3-spanner of this network, and now in practical settings, nodes in a network may fail. Now the problem is, if this was the spanner we constructed, and now one node fails, our spanner is no longer useful, because basically these 2 parts of the graph are not even connected anymore. So it makes a lot of sense in a lot of practical situations to construct spanners that can tolerate a certain number of failures, and in particular vertex failures in this talk. Specifically, a graph or a subgraph, depending on whether we're talking about an emulator or a spanner, for G is F-Vertex fault-tolerant for a parameter T if for for every possible fault set F of size small f, after removing this fault set F from H, we still have a T emulator or a T spanner of G minus F. And in non-faulty settings, we know the optimal size and stretch trade-offs, but our goal here is to see how does the size of the emulator or the spanner depend on this parameter F. And the other question that we need to answer is how do we set the weights of the emulator edges that are not in G? So for spanners, it's very clear. We're just maintaining a subgraph. But for emulators, we are potentially adding some new edges. And the question is, what weight do we give them? And let's see what our possibilities are and what makes sense to be the weight of the emulator edges. So remember that the goal is to make sure that this holds, that for any edge, the distance between the endpoints should be at most t times the distance in G minus F. So what are our options? In a lot of classical algorithms for emulators, we always set the weight between a pair of nodes U and V to be the distance between U and V in the original graph. So let's say we do this without taking any faults into account, and we just set the weight of an edge UV to be exactly d sub G UV. But the problem is, in this case, any fault set that changes the distance between an U and V is going to cause a correctness problem. Because in G minus F, we're going to get an underestimate of the distances if we keep the distances to be fixed. Okay, so this doesn't quite work. So the other option is to basically allow for the distance to for the weight to change after faults. What I mean by that is, consider UV edge that is an emulator edge that wasn't in G, and now consider faults at F, and we define the weight of this edge to become the distance in G minus F. So we basically update the weight after the faults happened to be the shortest path. And if you think about it for a minute, this is really the only natural option. Because as we discussed, if we set the weight to be a fixed weight, it could violate the correctness as soon as faults happen later. And we also can't set it to be a smaller weight than the distance after faults, because again, this will cause a correctness issue. It will lead to underestimates. And it also doesn't help us to set it to be a weight larger than the distance after faults, because there's no existential benefit. And if for some reason, for computational reasons, we do this to get more efficient algorithms or something, we can still adapt our analysis. Okay, so this is our definition of fault-tolerant emulators, that we can update the weights after faults. Okay, so let me also give you a practical motivation for this definition. So what emulators really are in the context of networks and distributed systems are what is known as an overlay network. What is an overlay network? It's a set of logical or virtual links between nodes in a network. And in the context of routing, these are basically exactly like emulators in many scenarios. So let me give you an example of how these logical links work for routing. So let's say I want to route a packet between node E and node G in this network, and there is this logical link or an emulator edge between these two nodes. So what the routing protocols would do is they would basically send the packet along the shortest path between these two nodes. So what really happens in practice is that the application-specific routing protocols really send the data along the shortest path between endpoints of a logical link. And they would do this automatically after faults. And this is exactly what an automatic weight updating would do. And basically the quality of the routing would depend on the stretch or the quality of emulator or this logical network that we've constructed. So this weight updating, even though it may seem kind of new and strange, it makes sense both theoretically and practically. Okay, now we've given a definition of emulators in fault-tolerant settings, and let's move on to an algorithm for constructing emulators and what our results are. So, as I promised, we see that we can construct better emulators in fault tolerance settings than we can construct spanners. And our results and comparison between emulators and spanners is summarized here. So what we know for fault tolerant spanners by now is that we can basically get an optimal size fault tolerant spanner of size roughly n to the 1 plus 1 over k times f to the 1 minus 1 over k, where f is the size of the possible fault sets. And what we show is that for emulators, we can at least improve this size with up to square root f for even k. And for odd k, we go further and get a bound that basically matches a lower bound that we also show. So we basically get an emulator with this size with respect to f, which is optimal for odd k. So of course the first question that comes to mind is, what's going on with this odd even difference? The question is it an inherent difference? Because it also appears in the context of edge fault-tolerant spanners. And by edge fault-tolerance, as the name suggests, instead of vertices, edges can fail. Another thing to note here is that our goal is to optimize the dependence on f, but in our algorithms, the dependence on k is not great, and in particular, it's exponential in k. So another question is, how can we eliminate this dependence? But interestingly, for additive emulators, we get even more surprising improvement in the fault-tolerant case. And in particular, we get additive emulators that are exponentially better in size than their spanner counterparts. This is because we know a lower bound for F-Vertex fault-tolerant additive spanners with additive error C for any constant C. And the way you can interpret this is that, for example, for any set of faults of at least size log n, we need n squared edges, so there's no hope of sparsifying and getting an additive approximation. But in the context of fault-tolerant emulators, we show that we can get optimal algorithms for +2 and +4 emulators that are exponentially better with respect to this dependence on F. And you see the bounds here, and the algorithms are pretty simple, but the important takeaway is the message that we can do things for fault-tolerant emulators that we can't for spanners. Okay, so let's move on to algorithms next. So let me start by a non-fault tolerant algorithm for constructing spanners. It's a well-known algorithm called the greedy algorithm, and then I'll explain how we extend it to the faulty case. So this algorithm is pretty simple and it's existentially optimal, and this is how it works. We're given a graph G and a parameter K, and we start with an empty spanner H, and then in non-decreasing order of weight, we process edges, and for each edge UV, we'll look and see if between U and V there's already a path that has length at most 2k minus 1 WUV. So if that's the case, then we don't need this edge, so we will ignore it. Otherwise, we add this edge. And if you have an unweighted graph, the ordering of edges being processed can be arbitrary. So let's see a simple example. Let's say we want to construct a 3-spanner, and this is a graph we have. So we start with an empty graph. Now between V1 and V2, there's not already a path, so we need to include this edge in the spanner. V1 to V3, we don't already have a path of length 3, so we include it. Same with V3, V4, but when we get to V2, V4, there already exists a path of length 3, so we don't need to add this edge, and same with V2, V3. So we have a simple 3-spanner for this graph. Very briefly, it is easy to see why this algorithm is correct, in a sense that every edge that we don't add, it's because there's already a path of length 2k minus 1. Let's say we're looking at an unweighted graph. There's already a path of length 2k minus 1 there, and for any shortest path, we can just look at all of these paths together, and we get a 2k minus 1 stretch guarantee. I won't get into the details, but the size analysis is also based on the fact that this graph doesn't have any small cycles, and we can argue that a graph with no small cycle has at most n to the 1 plus 1 over k edges. But let me go to the faulty setting, and let's see how we can change the algorithm to make it fault tolerant. This algorithm was first proposed by Bodwin et al. At SODA 2018, and it's the same as the algorithm described. We again process the edges in the non-decreasing weight order, but the difference is here when we consider an edge UV, we need to check and see if there's any fault set F of size at most F that basically forces us to add this edge. So is there any fault set F such that the distance after we remove the nodes in F becomes larger than 2k minus 1 times the weight of UV? If there exists such a fault set, then we add edge UV to the spanner. So clearly we are adding more edges because this fault set is forcing us to add more edges. Okay, now this was an algorithm for spanners, so what do we do to turn it into an emulator algorithm? As discussed, we should somehow utilize the fact that emulators give us some more flexibility because we can add new edges somewhere in the algorithm. So the other thing to remember is that the weights of these edges that we add that didn't exist in G can also be updated after faults. And I'm going to give you an algorithm for 5 emulator because the general algorithm is much more involved and it requires new definitions, so I won't get into it. And the idea here is that whenever we add a spanner edge UV in the greedy algorithm, we also sample a set of emulator edges, like the edges that are potentially not there, corresponding to 3 paths that have UV as a middle edge. And in the weighted case, UV has to be the heaviest edge on this path, but don't worry about those technicalities. So here's how the algorithm looks like. Same as before, we start with an empty subgraph, and we have a parameter D that depends on F. And now for, again, we go through edges in non-decreasing weight order, and we see if for an edge UV there exists a fault set that forces us to add this edge. If we add an edge UV, then in addition to UV, we add a sampled set of emulator edges as follows. We look at neighbors of U, for example S, and neighbors of V, for example T. We consider such ST pairs, and we add an emulator edge between S and T with probability 1 over D squared. So this is really what is different in the emulator algorithm with the spanner algorithm. And you'll see that it will be helpful to consider 2 types of edges in H. The spanner edges, which are the edges that already exist in G, and the emulator edges, which are these new sampled edges. They kind of have different behaviors in our algorithm, as we will see. So this algorithm does something counterintuitive, because in a sense we're saying whenever we're adding spanner edges UV, we're going to add emulator edges in the same vicinity. But intuitively, this helps us because these additional emulator edges that we're adding kind of help us reduce adding more spanner edges later. And also, in case of F fault-tolerant spanners, what we really want is to make sure that we aren't adding more than roughly F paths between any pair of nodes. Like, if we want a sparse graph, that's what we should do. We shouldn't add more than roughly F paths between any pairs. And somehow these emulator edges along these 3 paths will help us not add too many edges. So very briefly, correctness is again easy. I won't get into it. The size analysis is more complicated, and the idea is that remember we are adding these emulator edges based on the sampling probability, and somehow the way this sampling works is that we can ensure that for any pair of nodes S and T, there's roughly F3 paths that we are sampling from, and we can use this process to charge the emulator edges added to the spanner edges added. So in our analysis, we can bound the number of emulator edges that are being added based on the number of spanner edges that are being added. And then the path counting, like we count the number of 3 paths that we could sample from, and somehow we can use this to bound the number of spanner edges and hence the number of corresponding emulator edges. So, of course, we wanted to also give an algorithm for general K. I won't get into details of it because it's more complicated. We have to define certain set of paths with certain properties, and then the sampling probability will depend on the length of these paths. I skipped this algorithm for this talk, but let me finish by some remarks on lower bounds and polynomial time construction. So I briefly mentioned the Erdős-Gert conjecture, which was saying for any integer k, there are graphs with girth at least 2k plus 2 and at least n to the 1 plus 1 over k edges. So this is a well-known conjecture, and it's proven for some values of k. But using this conjecture, we turn it into a lower bound for constructing k emulators, 2k minus 1 emulators, and basically show that we need at least roughly these many edges. And the instance is not very important, but at a high level, we start with a Gert's conjecture graph and we do some transformation. In particular, we replace each edge with a bipartite graph of roughly size square root f. And then we have to reason that emulator edges can only replace a constant number of spanner edges. So more or less the overall number of edges we have to keep in this instance is around the original number of edges, which was which gives us this bound. Finally, the other thing to note is that the algorithm I gave you takes exponential time because for each edge UV, we need to check n to the f possible fault sets when we decide whether to add the edge. And this is exponential in f, so this is not desirable. And to make this algorithm polynomial time, we use ideas by Dinitz and Robel, which basically lead to a polynomial time algorithm at some additional factors of k in the size. And at a very high level, the idea is to replace this n to the f time procedure with an algorithm that approximates the smallest fault set f that causes the distances to go above the threshold. And this approximation algorithm is what adds some additional factor in size. Okay, let me conclude. I described an algorithm for constructing vertex fault-tolerant emulators and also mentioned a matching lower bound with respect to fault size f, but this lower bound matches the upper bound only when k is odd. So the first open question is, can we close this gap for even k? And as I mentioned before, this is also unresolved for spanners, but for edge fault-tolerant case, so maybe we should answer it there first. The other natural question is, what happens if we consider edge failures instead of vertex failures? Can we get a better size dependence on the number of failures in that case? And the other question is, can we improve the dependence on k in the size? And finally, another question is, what can we do for other related objects? Like, can we use similar ideas to construct, say, fault-tolerant distance oracles or other objects that are related? And with that, I finish this talk, and thank you. Please contact me with any questions you might have.